Hi, welcome to chapter 4 titled The Processor. And in this chapter, uh, what we will do, we are going to talk about the design of the processor, the detailed design of the processor, in particular, the sequencing of events that happens in the microprocessor. And for that, what we will do, we are going to assume a simple subset of instructions. We will design a processor, MIPS processor, but we will use a subset of the MIPS processor. We are not going to do all the instructions because really doing the entire thing is going to be very detailed, but we will pick one instruction of every class, and inside that class you can extrapolate the design to all variation of that instruction. So we will do load word, store word, add, subtract, and or set if less than, branch if equal, and jump instructions. So bit of memory reference, bit of arithmetic and logical instructions, bit of control transfer. Okay, so this is the goal for this chapter, and we will do different flavors and variation. We'll do scalar, we'll do pipeline, and see how this is implemented and all the issues associated with it. Now, if we look at any at the instruction execution, um, you will see that um, the instruction first is fetched from instruction memory. So in our system, we assume that we have two memories, instruction memory and data memory. What is the difference between the two? Well, the instruction memory saves and stores the instructions, and the data memory saves and stores the data. And why we have the two of them separate? Reason is that we want to access instructions and data at the same time, and thereby we physically separate them. Okay. Um, then we have the other component that we will use is the register file. Those registers that we talked about in chapter 2, S1, T0, RA, all these registers are housed or located in the register file. Then we're going to have an ALU, and the purpose of the ALU is really to perform the addition, the logical operations, subtraction, etc., etc. Also, we are going to need the PC, which is the program counter, which points to the instruction to be executed. So we send this value of the PC to the instruction memory and therefore and fetch the instruction to be executed. This program counter need to be updated either by +4 or by the branch instruction. Now, this is a very simplistic sketch. There are many issues that we need to address. Some of which um, we have. Sometimes we need to write to the register file, and this is for example when we save the value to the register, one of the registers. How do we do that? Sometimes the destination register based on the format is specified by bit 16 to 20 or bit 11 to 15 based on the format. How do we resolve these two? How to determine the correct destination of the destination register? Um, Sometimes the right value that goes to the register, the destination register, comes from the memory. Sometimes it's an output of ALU. How do we resolve that? Which one is which? Should we write to the destination register from the ALU like an add instruction, or should we write to the destination register from memory in the case of a load instruction? Okay, memory. Sometimes you need to activate read in the case of load. Sometimes you need to activate a write to the memory in the case of a store. So how do we resolve which type of access we need? Also, we have various types of ALU operations. The ALU second source can be from register, or in the case of an immediate data can be inside the instruction. Branch instruction, love try to change the PC in a different way. Well, PC normally updated as PC plus 4, but the branch instruction updates it as PC plus 4 plus offset. Well, how do we resolve this? The jump instruction totally different. Now, with these are some of the questions that when we design a processor, come up we need to come up with a solution to address these questions. Now back to this image where we have we can now improve on it and say, you know what, when we are doing updating the PC, yes, it's PC plus 4 here, but sometimes we need to have PC plus 4 and PC plus 4 plus offset, right? And this offset comes from the instruction. This is in the case of branch, Okay, well, which one to choose? PC plus 4 or PC plus 4 plus offset? Again, when we send back data to register file to be saved, is this the output of the ALU, or is it the data that we read from memory? Which one? Now, to resolve, whenever you have this kind of data, multiple source of data, and you are going to one point, the best thing we can resolve is to use a multiplexer, because in the hardware, that's how we select data. And therefore, we can update this drawing by the following. We say, you know, we have to have a multiplexer here to choose between PC plus 4 or PC plus 4 plus offset, okay, to update the value of the PC. Well, what's the select for this multiplexer? Well, the select, if I have a branch instruction and the branch instruction is accompanied with the 0 flag, because typically when I say branch if equal, okay, two registers here, I compare these two registers and they are equal, okay, basically 0 flag, and I have a branch instruction, then I need to select PC plus 4 plus offset. Otherwise, it is PC plus 4, which is the next instruction. Why plus 4? Because the next instruction typically saved after 4 bytes. Every instruction is 32-bit. The next instruction is after 4 bytes. So that's the address for the next instruction in the instruction memory. Now, again, in terms of data coming either from the memory in case of load or result of ALU in terms of ALU operations, we need to select which one needs to be saved in the register file. Okay, so we need a multiplexer here. Okay, and sometimes the second operand in the ALU is a register from the register file or immediate data from the instruction. Like, for example, in the case of add immediate, okay, S1 and S2 and let's say 4. This is immediate data, and this 4 is from the instruction itself. Okay, so now you can see what I have used, multiplexer, to resolve the issue of data selection, which data I need to select. Okay, so that will now we need to build our data path, right, piece by piece. Now we are building the data path here. Okay, now So you can see in terms of fetching the instruction, we are going to revise we are revisiting this. We say that the PC points to the address of the instruction need to be fetched. That address goes to the address of the memory, and the memory, what it does, it produces the instruction to be used in the CPU. Now this is the instruction memory. Observe that this instruction memory is a read memory. Okay, now for our program, obviously this memory is written typically by the OS, by one of the programs in the OS. It's called the loader. But when you execute a program, the program itself cannot write its instruction memory. It can only read from it. Okay, now once I read an instruction, I need to move to the next instruction. The next instruction is PC plus 4. Why 4? This is 4 indicates the address increments by 4, and the instruction memory is byte addressable. So when I add 4, it means I'm adding the addresses of 4 bytes, which means move to the next 32-bit. Every instruction in this machine is a 32-bit instruction. Okay, all right. Now, in terms of the R format, and when we say R format, it means ALU instructions without the immediate data. Okay, you can see I need this register file, and the register, I can send the address of 2 registers, since I can have 2 sources, right? And here comes the data for these 2 registers. This is the data for this register, and this is the data for this register. Once I'm done and I need to write back, I set the data here, and I specify the address of the destination register. The ALU can perform multiple operations, and therefore I have to tell it which operation I can do. And we have seen this in the last chapter, where we built our simple ALU, and we have these control signals, right? So this ALU is 4-bit control signal, which tells the ALU what to do: add, subtract, or etc. Okay, and this is my data memory. This is the component. So we looked at the instruction memory, register file, updating the PC, and then the data memory. The data memory, what it does is it houses the data, and I can write to it, I can read from it after I provide the address for whatever I need to read and write. It has 2 control signals, which tells me either to read from the memory or write to it. It's kind of redundant. Why do I need to have 2 control signals? Well, because sometimes I'm not doing a write, neither I'm not doing a write, neither a read. So sometimes I am not doing any of those. Like for example, when I'm doing an ALU operation, R-type instruction. In that case, both of these control signals are deactivated. Okay, sometimes I need to do a sign extension. And sign extension means whenever I have immediate data, part of the instruction, it is 16-bit. But and I need to forward it to the ALU. But before I send it to the ALU, I have to sign extend. Let's explain what sign extension here. Suppose I have this signed number, and this is a 4-bit. Okay, and suppose I need to send this 4-bit number into an ALU, which typically performs operation on 8-bit. Right? Before I send this data, I have to sign extended. And sign extend means you look at the sign bit and copy it 4 times. So now you have, this is 8-bit. Now it can be used in an 8-bit ALU. So sign extension mean copy the sign bit, in this case 4 times, and in this case 16 times, so that the data width will be 32. Now, the branch instruction, typically we say that the branch instruction it computes the branch target, which is PC plus 4 plus offset, and this offset is part of the instruction. So this is my instruction. Part of it is the offset, which is the 16-bit. Okay, so this offset comes in. We sign extend it to 32-bit from 16, and then uh, 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 we do a shift of 2. And the reason we do a shift of 2 because this is here. It is in the instruction. It is the address. It is word. Okay, it's a word address, and we need to convert it to byte address. And for converting from word address to byte address means that we need to multiply by 4, or a left shift. I'm sorry, a left shift of 2 positions. Okay, so that we convert it from words address to byte address. Then we add and we create the branch target. Now, so let's take a look at our ALU, where we need to do ALU operations and load and store. This is the instruction coming from the instruction memory. I'm going to specify the read registers. Here are the values for the read registers. They go to the ALU. The ALU produces the result. Okay, and then we go back here and we save the data back to. Okay, now what if this is a load instruction? If it is a load instruction, then the output of the ALU is the address of the load or the store instruction. Okay, so in the case of a store, I have the data coming to me here. Well, in the case of a load, I don't have any data. I will take my data from the memory, goes through the mux, and then back to the written to the register file. Okay, now notice that sometimes for operation with immediate data, like for example add immediate S0 S1 S, let's see, S1, let's say 14. This 14 is immediate data, so we send it to the second operand of the ALU. So the second operand of the ALU can come from register file or can come from the instruction. To select, we use this mux and this selection signal, which is ALU source. Notice the memWrite active during store operation and memRead active during load operation. Okay, during load operation. Okay, what else we need? The register write is active when we write to the register file, and the ALU operation tells the ALU what to do in terms of subtract and subtract, add, logic operation. Mem to reg tells me if the data is coming, the right data, the data that I save in the register file, is it coming from the memory or it's coming from the ALU. Okay, so it selects one of them. Okay, so here is our full data path. Okay, so let's review here. This is my PC value, the updated. This PC value can be PC PC plus 4. Okay, all right, so this can be PC plus 4. See if I, oops. Or PC plus 4 plus offset, right? In terms of branch. Now we use a multiplexer to select one of these two values, okay? And we use a select signal called PC source. Then we get the correct value of the PC and we load it to the PC. We access the instruction. The instruction has the address of the read register. read register and read register 2 and the address of the destination register. We read the register 1 and register 2 can be either from the provided data, and this is for the second source for the ALU. It can come either from the register file or it can come from the instruction itself. Okay, and we use ALU source to determine this coming from register file or from instruction. Now the ALU performs its operation and produces the result. This result can be either address to the memory in case of load or store, or the result that I need to save to the register file. So in case of I have a load or load, or I might have a result from the ALU, I use mem to reg control signal, which selects the appropriate data to be sent back and saves in the ALU. The mem write is active when I save data to the memory. Mem read is active when I load data from memory. ALU operation tells the ALU what to do. Okay, and reg write is active whenever I save data to the register file. This is my full data path. Okay, now the ALU is supposed to do multiple operation. So in the case of a load, right, we have to do an add operation. Add, why add? We need to add. So for example, when I do load, let's say for example T0, S0 and 4. So we need to compute the effective address. We add the base register S0 and 4. So we need an adder here. This needs to be added. So that's why I need an add for the load and an add for the store to compute the memory address. In case of branch of equal, we need to subtract, branch of equal, subtract the two registers. So for instance, if I have branch of equal to T0, T1, all right, and L1, I have to know if these are equal, and the way to do it is to subtract one from the other and detect zero flag. That's why we need a subtract operation for branch if equal. For the R-type operation, ALUs, for the add, we do an add in the ALU and subtract in the case of subtract, and all these we can take their values from the funct field in the R format. Okay, so notice here I produce these ALU control signals that tells the ALU what to do, add or subtract or ANDing or ORing or set if less than. Okay, now we can he's trying to remind me here with the fields of the R-type format and the I format. So this is the R and this is the I. Okay, notice that these are the opcodes here. Okay, these are the opcodes, right? And here's the funct, the shift amount in the R-type, and this is the RS and RT in the I format. Okay, and he wants to tell me that, notice that the destination register can be specified in different fields for the different format. Okay. Now, this is my data path with the complete control signals. Now, notice what we have here. First of all, this is the control signal which activates selection of either PC plus 4 to update the PC or the PC plus 4 plus offset. Okay, and that comes from where? We have a control signal called branch, which is active if I am executing a branch instruction, and the zero flag. If both of them are ones and the output here is 1, it means I need to select branch PC plus 4 plus offset. Otherwise, the PC will be updated as PC plus 4. I take this value and update the PC, access the instruction accordingly. Now notice here there is a control signal here. Let's choose a different color here. This control signal here, which tells me the address of the destination register here. the destination register based on the format can come from the 16 to 20 16 to 20 bits of in the instruction, or 15 or 11 15 bits in the instruction based on the format. So that I have to tell this multiplexer how to select for me the address, the right register address. Okay, now these are the mem read and the mem write. These are the control signals here. This is the mem read, and this is the mem write. Okay, mem write right here. Okay, and those basically, these two control signals, they are active: the mem read during load, mem write during saving data to memory. Mem to register, do a different color here. Mem to oops, that's not going to do any good. Uh, mem to reg here, it tells me that the data that would be saved in the register file either coming from ALU or coming from the memory. So we need to select for this multiplexer. ALU up here, ALU up comes from the instruction, and from it we can tell how to inform the ALU. Do we need to do add, subtract, set if less than, ORing, ANDing? So we have to decipher this ALU up and send the appropriate control to the ALU. This ALU source signal here, it tells what is the second source for the ALU. Is it from the register file, or it is from the instruction after sign extension? Okay. The read write is a control signal that is active whenever we need to write data to the register file. Okay, now with this is the data path with the control. Now you can see here, when we execute this R-type instruction, which is ALU instruction, comes in here. Okay, and I can get the address for the first and the second source of data. Here's the first data comes from the first register. Second data comes from the second register. We go through this mux, right? And then we produce the result of the ALU, and we go over here and we go through this mux back to the register file. And here we have the address of the destination register, and then we save the data in the ALU. Okay, notice how the multiplexer are the multiplexers are activated. Like for example, this one, okay, and this one. All right, so they activated appropriately for the data to flow correctly. And now in the case of the load, okay, in the case of the load, we have the first register, right, comes in here, and this data sign extended and goes here, right? So here the two registers, the register is added with the immediate data. So this one here is our base register basically, with the data, which to compute the address, and then we access the memory, right? Then we get the data from the memory. The data we go through the multiplexer, go back all the way here and save the data. Watch how the address of this destination register comes in and tells the register file the address of the destination register. This is in terms of load. In terms of branch on equal, I access the two register, and then I send them to the ALU, compare them here, okay, and if there is the zero detect, I'll send it over here to modify the PC plus 4, or plus PC plus 4, or PC plus 4 plus offset. Okay, now notice this this immediate data or offset goes in here and extended and goes through the ALU, so that I can compute PC. Oops. This is PC plus 4, and here I have the offset. So I can here have PC plus 4 plus offset, and I would choose one of them and send it all the way to the PC based on if this of course if this signal is 1 or not. Okay, the jump instruction is another story, because the jump instruction we need to compose the final address, and the final address consists as follows. Here is the jump instruction. We have oops, see the jump instruction. Here's the jump instruction. We need to compose a 32-bit and save and oops 32-bit address and send it to the PC. How we compose this? The least significant 2 bits are zeros, because we are converting words to bytes. And I take 26 bits from the instruction. And then the upper 4-bit are from the current PC. The upper 4-bit from the current PC value. So these are 4 bits plus 26, that's 32, plus 2 bits, that's 32 bits. That's how I compose the address of the jump instruction. So for that, you can see here is an extra mux for the jump instruction. So here you can see that this 26-bit beta coming from the instruction, okay, and then I'm doing here a shift to the left, so that's where I insert the 2 zeros at the right position, the rightmost positions, two zeros, and then I take the upper 4 bits from the PC, the upper 4 bits from the PC here, okay, which is see, here is the 4 bits, okay, and then I take the upper 4 bits from the PC and I compose the 32-bit right here. And here either I would select whatever I computed earlier in terms of PC, or I select the address for the branch for the jump, and I need here a control signal here, okay, so you can, which tells me I have a jump instruction. Okay, so here we select either what we computed or the address of the jump instruction. Of course, here I computed PC plus 4 or PC plus 4 plus offset, and I send it to this mux, and this mux selects between the jump instruction or what I have computed earlier. Now I would clean up this mess here, to be honest, and I make one multiplexer, okay, where I have either PC plus 4 or PC plus 4 plus offset, okay, or I have the jump address. Okay, so just one mux. He's doing in two level muxes, and a little bit confusing, becoming a little bit confusing. Okay, we have some performance issues that we need to discuss, and we will leave those performance issues to later lectures and part 2. And thank you very much.